Here we have exercise 7 from lecture 4, and we have another inclined plane. So it's a 50-degree incline, so we're going to draw that in. The difference this time is they're pulling the load, which happens to be 40 kilos of brick, up the plane. So let's draw our incline over here, and there will be a slight change as to where I draw the vectors this time, so that it's easier to see the angles of the weight force as it gets broken up, from having reviewed the last slide, last video. So we've got our weight here that's sitting on our we're at 50 degrees. 50 degrees goes there, and then our weight force we will consider from the middle of the base of it where it touches the load, and we'll consider that probably about there, and this will be our weight force, and this forms a 90-degree angle here. If it's 50 in there, it will be 40 degrees in here, because the sum of the inside of the angles should equal 180, be 90 plus 50 plus 40 will be 180 degrees, and our weight force, which as is usual is equal to our force, not WF, FW, force due to weight, let's draw these back in here, is equal to mass times acceleration, which we should know by now, and this was our 40 kilograms. Which is 40 times 9.81, which is 9.81 is 392.4, and because this was in kilograms, this was in meters per second squared, we know that this should be in newtons. If it wasn't, you'd have to do some conversions on there to make sure that that was in kilograms and that was in meters per second squared, so you could change this set of units to become newtons. Now, same as last time, we're going to have a different x and y than what we're used to, and I'll put that in a different color. That'll do. Okay, I'll draw them on here. We've got our y, which could be where it'll be perpendicular to our inclined plane. You can either have it going up or going down, up to you. I usually leave my y's positive, and then because I did it downwards last time with the x direction, this time I'll do it up this way with the x direction. It won't affect your final answer, aside from if you're defining whether or not things have a force. So calculate the force in the rope. It depends if it's moving in that direction or in the negative x direction. It's only going to change the sign. Once we've done that, we can say that our weight force will have a component in line with the y-axis, which will be our force due to weight in the y direction, and to complete our vector, so when we add up these two vectors we should get back to our original vector, our force due to weight in the x direction, and this we expect to be a negative number. This we also expect to be a negative number. When we draw the line from here down, you can more easily see this in here is 90 degrees, and if we've used up 40 of 90 degrees, then the other part here will be 50 degrees. A bit of an easier way to represent it than the way I did it last time, but I record these videos ideally without having seen what the answers are, so you get all of my thought process with how to solve these. On that note, where are we now? We've got our weight force. We've shown where the component vector is going to be with regards to the weight force. Other than that, in this problem, we've got a rope parallel to the plane and they're dragging it up the incline. So there's going to be a force, which you could have FR for the rope or FA because they're applying a force up the incline parallel to the plane. Right, it's going up that way. And then, in a different color, usually, I will say they're moving it up the plane. This is my direction of movement. That's my velocity. If it's going up the plane like that, my friction force is going to be back the other way. It's going to be in the opposite direction to my velocity. And these forces should balance out because they're the only... Oh no, sorry. We've got our gravity is trying to pull it down, and the friction force is trying to slow it down. The applied force is going to counter those two. And then we've got our force due to gravity that is normal to the plane. It's perpendicular. To oppose that, to stop that falling through, we have the normal force. Actually, I won't draw it there. That'll get in the way. I will draw off to the side. We know that it's forcing up under there at that center point, but we can't see it. So we'll draw it in the same line as the y-axis, but just offset off to the side. And that will be our normal force. So our normal force we're expecting to be in the same size, opposite magnitude to our wave force in the y direction. If the rope wasn't parallel, if the rope was going straight up or at some angle, then part of the applied force would be in the y direction, which means that these would have a third component and part of it would be in the x direction. Now that we've got our vector diagram complete, because we can see where all the forces should balance out, we know our friction coefficient, so we'll use that in a calculation off to the side. Let's draw up this table. The only thing we should note is there is a constant speed. Let's write that down. Since there is a constant speed, the system is in equilibrium. So the sum of the forces should equal 0. Okay, as I said, I write it down differently each time so you can see different representations of what you could say. If you wanted to, you could say the system follows Newton's first law, where there are no unbalanced forces, therefore there's no change in speed, or there's a constant speed, therefore there are balanced forces. Up to you. Here we have our x and our y column, and remember these are all forces, so I'm not going to draw the velocity on there, I just know that it has a constant velocity. Down this way, down this way, and the first one we're going to look at is my weight force. It doesn't have to be, but it's usually the first one I pick. The force due to weight, which I've calculated the number for, which is 392.4 newtons. So my weight force, cos theta, my weight force, sine theta. Okay. I know this number, 392.4 cos, and my angle is what I've got to work out. My x-axis is here, moving towards my y-axis, and I'm trying to get to my weight force. So it's gone through 90, down here is to 180, and then I'll pick a different color for that. Blue. So from the x-axis, and I've drawn the axes pretty much on where I'm looking. It's going to go 90. There's a right angle in there. Another 90, and then 40 more gets me to my weight force vector. Okay, so we've got 90 plus 90 plus 40 is 220. So we should get 220 degrees in here. And that's going from x in the direction of the y-axis and then going all the way around. And that works out as a number to be 394 point, oops, let's not make the same mistake as last time, let's type in these numbers correctly. 392.4 cosine of 220 degrees is minus 300.6. So FW in the x-axis is, or the x component of FW is minus 300.6. And for our y component, 392.4 sine of 220, same angle, same size, just sine instead of cos. We get minus, so FW in the y direction, we get minus 252.2. That's FW done with. The next one we could look at FN, it's right next door. And we'll need to know Fn to complete that one. Fn, which we don't know yet, Fn cos theta, Fn sine theta, which will be Fn, because we don't know the size of it yet. When I draw my axes out, y-axis, x-axis, okay, this is 90 degrees from the x-axis going towards y, so our angle in there is going to be 90, cos 90, Fn sine 90. If you look at the solutions from Sanchita, she doesn't worry about all this table. She looks at it logically and works out that these two, FA should be equal to FF and FW, or the x component of FW, and just does a quick sum there, and that the normal force should be equal in magnitude but opposite direction to the weight force in the y direction. But I like my table, it works for me, and I can always double check everything's there, and when it gets more complicated I've still got the same process that I do. Cos of 90 should be 0. Cos of 90 is 0, so this works out to be 0, so Fn in the x direction equals 0. Visually that makes sense. Always check that all your numbers here make sense. Remember I said we were going to get negative numbers here and here because we're going in the negative y and the negative x. And then if this one is 0, this one has to be the full amount. And sine of 90 gives us 1, so Fn in the y direction is equal to Fn. Going down, we've got our applied force, and then I'll do the friction force. Fa cos theta, Fa sine theta. Okay, we'll just move it down a bit. We'll leave the coefficient of friction there because we'll need it. Fa cos of Fa is, I believe, straight in the x direction. That's our x, that's our y. So it's at 0 degrees. Cos of 0 degrees. Fa sine of 0 degrees. Okay, here we'll just have FA in the x direction is equal to FA, cos of 0 is 1, and FA in the y direction is equal to 0. Just stick our newtons on the end of there. Don't want to lose any marks for not having units. We won't put units there because we don't have a number to put it with. We could, but I won't, because it'll look, if I've got the letter there, I want to substitute something into it, and I might want to substitute something into it there, but when I've got a number, I'm going to have the unit there as a whole answer. Okay, FA's there, which we don't know yet, but we will be able to work out the friction force once we get to our sums at the bottom. FF, our friction force, cos theta, our friction force, sine theta. So we've got our friction force, and if I jump back over here and draw little axes over here, we've got x, y, and we can see that we have to go 90 degrees to get from the x-axis to the y-axis, and then another 90 degrees to say, instead of pointing that way, we've rotated around to point that way by 180 degrees. So I'll just clear that off. We could leave that one there. So cos 180 degrees and FF sine 180 degrees. And here cos of 180 should be -1, but I'll just double check. It's getting late. Yep, it's -1. So the friction force in the x direction, because it's telling me what direction is up there, is equal to minus the size of the friction force. Okay, remember the size of my vector here can only be positive because it's the length. Here I'm saying that the friction force in the x direction is in the negative x direction by the length of that vector, which is what I'm showing here. And friction force, sine of 180, in the y direction, sine of 180 is 0, so this will be 0 newtons. Yep. Remember, we're looking that the sum of the forces equals 0, and I've said why I want that to be true in this situation. So the sums of the forces, the sum of the forces should equal 0. So the sum of the forces in the x direction should equal 0. So I have minus 300.6 plus 0 plus FA minus FF. Oh, I've done it again. Instead of writing FF, no, I'll leave that there. This would also be equal to minus mu times Fn, because it's our formula over here. Our friction force is equal to mu times our normal force. So if we've got minus the size of the friction force, it'll be minus the size of Fn times mu. Just remember that this can only be a positive number, because Fn should give us a length and that should be positive, but in the case you've made a mistake, the number in this section should be positive. So as a result, FF in the x direction will be negative because the minus sign is outside of this part here. I might leave that just as FF. So we've got minus 306. I'll put in brackets to remind myself it's negative. That way I won't lose my minus sign. Plus 0 plus FA. I'll leave that here. So minus FF. But if you've done it the other way, you could always account for it there. make sure to always leave enough room for your sums. I never do. Equals 0. And I'm going to leave it there because I don't know which one of these I will have a number for. So I'll leave this there for the moment, and I'll work on the y side. We get the sum of forces in the y direction equals 0. So we have minus 252.2 plus Fn plus 0 equals 0. And here I will add 252.2 to both sides. So we get Fn equals 252.2 newtons. Okay. Now I know what Fn is. I can replace the friction force in here. So we'll use this formula. The friction force instead will be mu times Fn. I'll calculate it over here, then I'll drop that number in there. I'll substitute it in. We were told in the question that the coefficient of friction is 0.6. If we'd given you both static and dynamic, you would have to, or static and kinetic, you would have to see that they're hauling it up. Because it's moving, it'll be the kinetic friction. We know this is 0.6 from the question, multiplied by Fn, which we calculated over here, times 252.2, and that is equal to 252.2 times 0.6 is 151.32 newtons. Where are we? That's my friction force. My friction force is going to add to the weight force, which is the 300 there, so they should both be in the same direction, and it will be because it'll be negative this number. So just a little bit more room, still going down the page. Minus 300.6 plus Fa minus, well, plus minus, because it's negative and our friction force is over here, 151.32 equals 0. I'll just steal a bit more from this side. Let's add these two numbers together. Plus 300.6 is minus 450. I'll leave this as all the decimal points here, and then I might round it as my last change. Plus Fa equals 0. I'm going to add this number to both sides, so add 451.92 to both sides, which leaves us with Fa equals 451.92, and I might just round that to 452 to 3 significant figures. That just says that I've rounded it to that many significant figures, and it should be in newtons. So the applied force, the force in the rope, because this just says Fa, at no point I've said Fa is the force in the rope, so I have to put a little sentence over here saying the force in the rope. I should have up the top said let the force in the rope be represented by Fa. Force in the rope was found to be, or was found to be 452 newtons. And then when I double check my answers off to the side, so I don't have to join up videos when I find that I'm wrong, this one, I find that we have 452 newtons as the answer. And that was done with rounding earlier on. Here I've rounded as the last possible thing. Thank you for listening.